In this video, I'll show you how to solve the ALEKS problem called predicting whether molecules are polar or non-polar. So in order to solve this problem, we're going to need to draw the Lewis structures of all of the molecules in the problem. Or you can just look the Lewis structures up on the internet if you don't feel like drawing them. I'm just going to draw them all really quickly. There's HBr, and next is H2O. It's important that you include lone pairs when you're drawing these structures. And then last but not least, CCl4. So this is a good example because there are three different, pretty different types of molecules in this particular problem. So that's nice because you'll get to see a variety of different scenarios for this problem. So one thing you want to look for right away, if any of the molecules that you're working with have only two atoms in them, like my HBr molecule has only two atoms in it. These are definitely the easiest ones, so you should start with this one. If the two atoms are different from each other, like I have an H and a Br, the molecule is almost certainly going to be polar. The only situation in which it might not be polar is if the two atoms are really close together on the periodic table, like if they're side by side. If they're super close together on the periodic table, it can be a little bit difficult to predict if they're polar or nonpolar. In that situation, what you want to do is look up the electronegativity values of the two atoms in the molecule. So you would look up the electronegativity for hydrogen, look up the electronegativity for bromine, and if the difference in their electronegativity values is 0.5 or more, then the molecule is polar. If we have a molecule that's polar, like HBr, and I don't feel like I need to look those up because HBr, those atoms are nowhere near each other on the periodic table. If they're super far apart, you can just assume that it's polar. The other question asks us to predict which atom is closest to the negative side of the molecule. That's just asking us to predict which atom is the most electronegative, and that's just based on the trend for electronegativity. The electronegativity increases as we go up and also as we go to the right. Bromine is further on the right-hand side of the periodic table, so the atom that's closest to the negative side is going to be the bromine atom. And so again, this is the approach you'll take if you have a molecule that has only two types of atoms on it, only two atoms on it in it. Now, the other example, the next one I want to jump to is CCl4. This is another type of example that you could encounter. CCl4 is a molecule that is just perfectly, completely symmetrical. So if we're looking at our central atom, all of the atoms attached are identical. It has all chlorines, so it's not like it has some bromines with some chlorines. All of the atoms are exactly the same. And then also notice there are no lone pairs on the chlorine atom. So I'm just going to kind of make a note of this. We have no lone pairs on our central atom. And also all of the outer atoms are identical to each other. And for a molecule like this, and it doesn't matter what the atoms are, if you have no lone pairs at all on the central atom, and all of the outer atoms, all of the outers are identical to each other, that molecule, because of its perfect symmetry, is nonpolar. Now, this is telling us that we only have to answer this question about the negative side if the molecule is polar. So since this is a nonpolar molecule, we don't have to answer this part. Now, the third type of molecule I have in this set of examples is water. This one is a little bit trickier. This is a molecule that does have lone pairs on the central atom. And also, even though both of the outer atoms are identical, it's possible that you might encounter an example where your outer atoms are different from each other. Maybe there are lone pairs present, maybe there are not, it doesn't matter. So whether or not, as long as you have more than two total atoms and you don't have this exact scenario where you have perfect symmetry, if you have a problem like that, then we're going to have to think a little bit more detailed about whether or not the molecule is polar. And the easiest way, in my brain, the easiest way to think about this is to imagine the molecule in its three-dimensional shape. So three-dimensionally, because this molecule has a total of 4 areas of electrons around it, it has a tetrahedral shape. The tetrahedral shape is something that we like to draw kind of like this. All of these bond angles are 109.5, or maybe they're angles between bonds and lone pairs, things like that. So this angle is 109.5, and also the angle between the hydrogen atom and the lone pair is also 109.5. Because this molecule, even though it does have like a plane of symmetry, we could imagine drawing a line right here, and the left half of the molecule is exactly the same as the right half. But the molecule doesn't have total symmetry. There are places where we could draw a line and there isn't symmetry around that line. So if we drew a line right here, this side of the molecule is not symmetrical with the other side. If we can find planes of asymmetry in the molecule, places where the molecule is not symmetrical, that molecule is going to be polar. So this usually comes from the presence of lone pairs on the central atom, and the lone pairs are not exactly 180 degrees apart from each other. So they're 109 degrees apart from each other, or 120, or something other than 180. If we have a polar molecule, then again, our job now is to figure out which atom is the most negative. So we have hydrogen atoms and oxygen atoms in this molecule following the trend of electronegativity. The atom closest to the negative side is going to be oxygen.